at the end of this month, and where we shall have also other people. You know, for us who have been listening to the same story, we shall have other people who will join us for that presentation, because it will be near completion. And today's presentation is to look at issues which were raised in the last presentation. And without taking much of your time, Ms. Christina Naviona is starting.
Thank you, Dr. Good morning, everyone. I'm Christina Naviona, Master of Science, Environment and Natural Resources. My title is Assessing Environmental Impacts of Geophysical Exploration Techniques, a case of exploration area 2 Albertine Graben. My supervisors, Dr. Nyakairo George and Mr. Robert Tugumi. We are all aware that oil and gas exploration worldwide has been on the increase. This is to take care of the increased energy consumption globally. Oil exploration has environmental risks attached with it, though these vary with the method of exploration used. And it has been observed that of late, most potential petroleum reserves are situated in ecologically sensitive areas. An example is our own Albertine Graben. It is an ecologically fragile area, but endowed with petroleum reserves. This study is coming in to see how we utilize our oil resources without having to endanger our environment, to conserve it at the same time. We use the oil resources and conserve the environment at the same time. Geophysical exploration aids subsurface mapping. It identifies geological structures and pinpoints where drilling should take place. So the knowledge gap that has been identified in the Ugandan case is lack of a template or a guideline to acquire geophysical data in the Albertine Graben. This is what the study is coming in to address. Geophysical exploration is the application of geophysics techniques to identify and study geological structures. We have active and passive methods. Active methods involve the introduction of artificial energy waves into the subsurface, such as seismic energy sources. Passive methods take advantage of the potential fields of the Earth, such as the gravity and magnetism of the Earth. So changes and differences in gravity and magnetism can help in mapping and identification of geological structures and basement rocks and sediments. The general objective of this research study is to make a contribution to the environmental management of geophysical exploration surveys for petroleum exploration in the Albertine Graben. The specific objectives. Objective number 1 is to predict the potential environmental impacts associated with an acquisition method and establish the relationship between impact severity and acquisition method. The second is to assess the environmental risks of the predicted environmental impacts and establish risk levels in the different acquisition methods. The third is to assess the environmental risks of the predicted environmental impact and establish risk levels across the exploration methods. The third is to compare and contrast the utility of the various geophysical methods in achieving exploration goals. The comparison will be based on environmental risks and data quality. These are the research questions. Can we acquire geophysical data in an environmentally sensitive area? What are the potential environmental impacts of the geophysical methods? Airborne, ground gravity, magnetic, and seismic methods. What risk levels are the impacts? Are they high, low, medium, tolerable, or intolerable? Which geophysical technique gives the best data and has minimal impact? hypothesis number 1, there is no significant difference in the impact severity for the geophysical exploration methods. The second is no significant difference in the environmental risk levels of the geophysical exploration methods. The third, no significant difference in data quality of the acquisition methods. And the fourth is there is no significant difference in the utilization of the different methods available. The study area is Albertine Graben Exploration Area 2 in particular. Area 2 is comprised of the Kaisotonia and Discovery and the Ulisa Discovery. It is approximately 4,885 square kilometers, located on the northern of Lake Albert. It is currently licensed to Total, Talo, Sinok in a partnership. Geophysical and environmental data was used for the research. Methods and materials used. The prediction of the potential environmental impacts, a checklist method based on expert opinion was used. For risk analysis, hazard based on the AS, or this is Australian, New Zealand, 4,360 method was used. And then to identify the tolerability or intolerability of the impacts, the RR, which is the as low as reasonably practical, HB436 was applied in this case. Data resolution, gravity and magnetic anomalies interpretation for geological structures, qualitative analysis of seismic sections for the amplitude and frequencies was used. This is a framework of the methodology. To assess a methodology in terms of data quality and environmental impacts, we first predict the potential impact of that method using the checklist method and the hazard risk analysis. You go on to look at the data quality in terms of resolution. Is it broad-based or scale-based? Broad-based, that is it identifying the basins, the geological structures, and small-based, small scale-based, is it pinpointing the areas that are drillable? After attaining that, compare and recommend which method should be utilized in which kind of environment. Data analysis, the chi-square test for independence between consequences, severity, and geophysical method was used. One way ANOVA with ranking for risk ranking, and then for comparing data quality t-test was used. Before any environmental predictions can be done, a baseline study of the area has to be done to understand the social, environmental, economic setting of an area. So from the literature on the Albertine Graben is endowed with biodiversity. It's shown it has historic and cultural sites, surface and groundwaters, air, soil. There are people who stay in the surroundings, they dig, they look after cattle. So we are going to evaluate how oil exploration methods, the geophysical oil exploration methods will impact them. And these are the impacts that we came out with, and there are frequencies to calculate the risk levels. Low risk levels 1 to 5, medium 6 to 12, then high 15 to 25. This is basing on the hazard, the Australian New Zealand standard 4360. These are the impacts and their risk levels. And this is a summary of the impacts per method. For seismic, a total of 35 impacts were identified, whereby 24 of the impacts were major, 10 were minor, and 1 was negligible. Ground geophysical, a total of 16. 9 were major, 5 were minor, 2 were negligible. Airborne had only 3 impacts, and all of them were negligible. So to assess the impact severity and method of acquisition, the chi-test of independence was used. The null hypothesis was there is no there is no association between consequence severity and method of acquisition. So the null hypothesis, the alternate hypothesis was consequence severity is dependent on acquisition method. We went ahead to categorize the impacts per method, as can be seen. These were the observed frequencies, and then the expected frequencies were calculated, whereby the chi calculated was compared to the chi tabulated, and it came out that the calculated was greater than the tabulated. In this case, we had to reject the null hypothesis, concluding that consequence severity is dependent on acquisition method. Risk ranking was done by one-way ANOVA by ranking. Null hypothesis was environmental risks are the same across all the 3 exploration methods, and the alternate was environmental risks are not the same across all the exploration methods. A ranking of the impacts was done, and then the total of the ranks for each method was given. Then the squares of these totals were found, and then the calculation for the ANOVA by ranking was done to get the calculated H at a degree of freedom 2, which was obtained from number of variables 3 take away 1, which is 2, at significance level of 0.05. In this case, H calculated was greater than tabulated, meaning that we reject the null hypothesis. So we conclude that environmental risks are not the same across the exploration methods. Then this is a gravity and magnetic map showing that the gravity and magnetic data can be used to get the geological highs and lows. Blue shows the basins that are usually structures of hydrocarbons, and then pink are the high places that are not of geological importance regarding the oil and gas exploration. Comparing acquisition methods in terms of data output per now and environmental risk, this is it. It's found that seismic has a higher resolution because it pinpoints small-scale structures, and it is able to show us where to drill. But then if not properly planned, it has adverse impacts. Free tensor gravity has fair to good resolution, but has minimal environmental impacts. Airborne magnetic and gravity gives broad scale resolution, meaning that it's not very high, but it's able to identify the structures as seen. It has minimal environmental impacts because it's airborne. Ground gravity has broad scale resolution. Environmental risk is medium. To analyze this data, a scale will be formed for the data output, and statistical analysis will be carried out. Discussion of the results. It was established that airborne methods have the least impacts in concurrence with Helen Anderson, who had done a similar study on airborne methods. And it was established seismic and ground methods have medium. That is, medium for seismic was 4 to 12, and then for ground 2 to 9. Number of events, as summarized in the previous graphs, were 35 for seismic, 16 for ground methods, and 3 for airborne. Most significant impacts was loss of vegetation and generation of solid domestic waste in camps of the seismic crew. Then ground geophysical methods has soil contamination as the most significant at a risk level of 9. Both risk levels are medium level and therefore require mitigation to be kept as low as reasonably practical. Ground geophysical has 3 consequence categories. That is 1, 2, and 3. 3 is the most frequent, with 9 events out of the 16. Seismic had the same categories, but with 24 events as major. That is in category 3 out of the 35. Although impacts predicted, none was severe or disastrous, which is worst. Conclusions. The major environmental impacts in terms of that: vegetation loss, domestic waste accumulation, visual intrusion, and that as can be seen. But then the major conclusion is that impact severity varies with method of acquisition, and the environmental risks are very different and significant in the different acquisition methods. Then in terms of data quality, seismic has the best resolution, and it has got the worst impacts, but it can be planned and carried out to acquire good data of the required resolution with minimal impact. This can be done by integrating the gravity and magnetic data to plan and come up with seismic lines to make sure that the group of seismic and the amount of seismic required is reduced. Way forward. We're going to use zero gravity and magnetic data from EA2 to come up with an anomaly map, and then using the existing 2D seismic, it will be superimposed on the anomaly map to show that, to demonstrate that gravity magnetic data can be used in planning seismic, and thus to minimize environmental impacts. Then a comparison of seismic sections of different energy sources will be done to establish maximum frequency per source and the penetration depth of each source. Very grateful to Tallow Oil for having sponsored me to ensure that this program took place. I'm grateful to my supervisors for the technical input and encouragement that they always provide. Thank you.
Thank you, Christine, for a good presentation. And so far, I see the good work has been done. But however, we have some few queries here and there. Please, you could, if you have questions, Christine, you ask, or you have a contribution or comment, so that it adds on the improvement of the work.
Okay, thank you. Maybe some comments. One is on your chapter, materials and methods. Is it methods and materials or materials and methods? They have to verify with the guidelines for graduate school. They mean something different. That one, yeah. Yes. The other one is you talked about the methods for risk level analysis. If you could maybe go there. You mentioned some of them. My query is, are there others? And if there are others, what criteria do you use to choose these ones, and why? Yeah. I don't know, maybe you ask them at the same time. The other comment maybe would be on when you doing your statistical analysis, you use the chi-square, the t-test. However, I'm not so sure which version, whether it's a capital T and then test, or it's a small t in Italy, then t-test, that one there. You may have to verify if it is really that t test, or it is a small t in italic, then test. Yeah, it could mean something different. The other one maybe is on, sometimes when you're presenting, you're telling us as if you're going to do the work that you have done it. For example, you said we are going to evaluate. Yet you've already evaluated. You move the next slide after this one here. That's it. Next. That's why you're doing your running the ANOVA. You say that you did the move that one. Risk running by one way, ANOVA by running. Is it, let's make some good sense to you, or it seems like there's some repetition? Risk running by one way, ANOVA by running. It could be like that. So maybe if you're sure it's like that, then you leave it like that. But if there could be another way of putting it, it would be better.
Yeah, it has another name actually,
Yeah, because when you say risk ranking by one way and not by ranking.
I think maybe I should make it one way and not by ranking.
Yeah, you say yeah.
Okay.
Not by ranking. Then, the other comment is on, you mentioned Helen Anderson et al. That way of citing, do you cite all the names or you just cite that one there? You just read say Anderson et al. 26. And from your findings, you did your findings and you mentioned what you found out actually. Which been the scope of your work to make a recommendation. You as someone who has done the analysis, what method would you recommend? Maybe if there are any constraints, you would also state the constraints in your recommendation. I recommend this, but in condition that this, maybe this is done like this or that. Then, if you go to the discussion slides, not this one here, the other one, move to the next one. Okay, yeah, that one. So the most significant impact for significant is loss of vegetation and generation of with that one. Did you take interest in finding out why with this method, why should it be loss of vegetation and all that, not maybe the elephants dying and all that? I think that's all.
So you could respond to those ones which need response. Thank you, Barnabas, for the critical comments.
About the materials and methods, I'm not sure. Yet I will confirm with the guideline. Then about the risk analysis methods, are there others and why I chose this particular one? Yes, there are others. For example, this is Australian and New Zealand. There is American standard and UK. Why I chose this? Because most journals were using this when I was reading papers and what. I think this is the, I don't know, should I say the one that is believed in most or what? But why I chose it, because it's the one I was seeing in journals, in most environmental assessment journals. This is what they use. That's why I went for it. And then the t-test, I think it is a small t, but yet I will read and find out what it is. It's about writing the t-test, whether it's capital T or small t. I will find out, I will confirm this. Then I've taken note of the tenses I should use as I'm presenting. I've already done the work, but then I've taken note of that. Then risk ranking, repetition, I've noted that repetition, I will correct it. And thank you on the citing, how I should cite. Thank you so much. Then on the recommendations, I'm going to take your advice as in to come up to explain why this impact came up as the highest for this method and why not this. I will read and establish why it was like that. Thank you very much.
More comments? Questions? Robert, John? No? Okay, thank you, Christine. And I would thank you that from the previous one, this is now near completion. And I encourage you that maybe as we are scheduling another interaction, you have completed all this. But I wanted to just on your specific objectives, the numbering, you had the 1, 2, and then was it 1, 3, 4? Eh? Can you go next? Go. Yeah, 1, 3, 4. Where is the second one? Oh, it is the.
You can't see it, but maybe it's there.
Yeah. And just as Barnabas pointed out, that chapter is the materials and methods.
Okay.
Yeah, materials and methods. First give us your materials and then the methods later. Yeah. Otherwise, thank you very much. Most critically, the citations and whatever, Barnabas had pointed them out. Thank you. And I hope this ECC is ready. It's about to be ready so that the near. Thank you very much. You join me to thank Christine for that. Next, we are having,
and this is my second presentation on the progress of my research, which is geochemical analysis of near surface sediments and oil seeps using mass spectral analysis, and the studies basically based in the Albert and Graben. Yeah, I'll go straight to the problem statement, which I have upgraded basing on the recommendations from the previous presentation. That the traditional geochemical methods for reconnaissance studies for hydrocarbon exploration have been found out to be time-consuming and very costly. And previously there has been a gap of integrating the remotely sensed data with the geochemical and the geological data. Because of the immense benefits of remote sensing, it will be applied in exploring viable information that will enable the economical exploitation of the oil and gas deposits. And the studied area is the oil seeps and the near surface in the Albert and Graben in the map are shown there. I'll go straight to the methods. The other time I presented some work on the color composites that I was using. So there are some additions as you will see here. And the other method here being the spectral band ratioing. So I have performed a number of ratios, and one of them being a band combination of 7/4 to 1. This band combination is very key in geological discrimination of different lithologies. As you will see from this image here, we have different colors. We have the yellow here, we have some red, the white being there, and some blue color here. All these ones represent different lithologies. But now when you go into the band ratioing details, we are able to actually come up with the exact meaning of these different colors. Now, a band ratio of 2 to 1, I used this band ratio and it was very effective in mapping out areas with the iron 3. This is the soil appearing brown naturally. So in the hydrocarbon affected areas containing high iron 3 content, they show that there hasn't been any alteration. So you'll see all these bright pixels here. All these ones are altered areas, and areas which contain the major alteration, I have tried to encircle them with this red color here. So you'll see them. However, there are other distributions like here, there, and there. All these ones show areas containing iron 3, meaning that they are not altered by the hydrocarbon migration. Now, another key band ratio was the 3 to 1. This one was very key in pointing out the areas which were immensely affected by the hydrocarbon migration, as illustrated by the circles in red. So these are areas containing a high concentration of iron 2. You know, the migration of hydrocarbons to the surface combines with the sediments and soils to react, forming the iron 2, as we shall see in our consequent equation. Yeah, I'll explain it chemically here. You know, we have hydrocarbons reacting with the sulfates present naturally in the soil and sediments to form hydrogen sulfide. We know in solution hydrogen sulfide dissociates to form acids, which are going to attack the iron 3 naturally present in soil as a brown color, and that brown color is formed by hematite. So when these two react, they form iron 2, which is this iron sulfide, the one I'm calling pyrite. So all those areas that we're seeing with dark pixels in this image up here are those ones that would have undergone the alteration as a result of the hydrocarbons being in place. So according to some literature, they say that the acids are resulting from the hydrogen sulfide, as we have seen before, and of course other reducing fluids present in hydrocarbons, they form a redox environment that's able to cause the immobile iron 3, the brown color, to actually be reduced to a more mobile iron 2, which could either be washed out of or leached out of the soil in the name of pyrite and siderite. Then I also performed a band ratio of 7:5 and 4:6. These two band ratios were used to actually map out areas which had clay alteration. Of course, the alteration resulting due to the presence of hydrocarbons. So you realize this is a band ratio of 7:5. It was better in mapping out areas with kaolinite being formed from the alteration of clay. So the bright pixels in this image here, you see all these bright pixels here represent regions with high concentration of kaolinite that's being formed from the alteration from clay. So this is an image of the 4:6 band ratio showing the formation of the kaolinite from the clay, as we see with a major alteration being in areas circled with red. So, like I've said, that the 7:5 band ratio was far better in differentiating the formation of kaolinite from clay. However, the 4:6 still gave us some results. So by comparison, the 7:5 was a better ratio in forming the kaolinite. So basically, the formation of this kaolinite, we see it in dark pixels in this image here, and this is basically due to the absorption of kaolinite at this particular wavelength. Therefore, when absorption takes place, the reflected energy or electromagnetic radiations are going to be reduced, and hence we are going to see a black color. So that's the reason. So this is the equation here trying to illustrate how the alteration actually takes place. We have our clay, which we are calling the K-feldspar, combining with this acid that's resulting from hydrogen sulfide to form the kaolinite here. At times, in those sediments which are altered, you may find there this mineral as well. So it's as a result of that reaction that takes place. Then this was my classified image, which I had shown previously in the other presentation, but however I was told to modify it, and I tried to insert in the names. So this is how beautiful it's appearing. And it was formed by supervised classification with maximum likelihood. Then the further work that I still have to complete now, I got a communication from PEPD about the geochemical and the geological data that I'm going to be getting. So I hope to incorporate between now, before we have the Dublin trip. And of course I'll be continuing with the data analysis so that come that time I'm able to go through. Thank you so much for listening.
Thank you, John, for the presentation, and as we must be having some comments, questions, clarifications. Please, you can bring them up.
Okay, I think I have some comments.
Yeah.
When you're starting the presentation, you mentioned that you asked us to remember the presentation of the previous one. I don't think it may be proper to ask the panelists to remember. Some of them have not been there,
Yeah.
and even those who are there may not remember. So I would ask maybe you give an overview. If it is cumulative from that, maybe give an overview of what you said, then you continue from there. Yeah. And maybe the other thing would be including the many slides that you don't even talk about anyway, then you keep people in between slides. I think that if you know that I'm going to talk about this, you only include those instead of including slides, then you keep, because some people may think there's something you're hiding there. Maybe you're not sure what you're going to talk about to them. Yes.
That's true.
Then maybe I would ask if there's a relationship between the band ratio and whatever you're mapping out. What do you say, okay, for this particular maybe elements, I'm using this band ratio and all that. Is there a relationship? Because you're using different band ratios for different, mapping out different, I don't know what you call them, elements, yeah. So is there a relationship between those elements and the band ratio that you're using to map them out? Yes, then maybe we have to check some chemical formula that you wrote. Some of them has CO2 in the same line, H2S, some slides. Maybe if you could go up and see. It's like down. That is the end. That one, yeah. Those one in the first bullet. Maybe that's how they are. I don't know if they exist. Yeah, that's briefly.
I'll start with the last one, maybe to respond to them. Yeah, like the CO2 and the H2S, that's because this is a PowerPoint, I try to reduce on the space. Because if I said it right, the carbon dioxide and the hydrogen sulfide, I'm going to find myself having a conjugation of
But the way they are written is like a subscript, the two, it's like a subscript, CO, then subscript 2. Then the H, subscript 2, then S.
Okay.
Yes.
I know that I'll try to work on that. And maybe the other question that you're trying to raise on the different band ratios, yeah, from literature, we know we have the electromagnetic spectrum, and if we come, for example, there, different minerals respond differently to the electromagnetic radiation. So when I try to make a band ratio maybe of 7:5 and maybe I make a 3:1, these are different regions of the electromagnetic radiation. So different band ratios represent different minerals. So that's that. That's why I formed those different band ratios. Yeah. So they help me differentiating between those different minerals that appear in the sediments. And I think that's that too.
Those were the questions.
Yeah, the other changes that I will try to make, like the CO2, I will try to correct them. Thank you.
Yeah. John, I have some issues because your presentation was basically not the whole presentation we expected, because you are presenting the corrections which we are given in the last presentation. If somebody was not there in the last presentation, couldn't follow what you are saying, and I hope that I want to urge you that the next presentation you make a full presentation as we are nearing completion,
Okay.
so that we could easily tell where we are lying, yeah. Because now you came with the problem modified, and then the band ratios, and then also labeling, so we can't know what is the rest where we are. So in the next presentation, please, you make a full presentation, okay, of the whole work, not the corrections. You get me?
Yeah, maybe if because I remember in the other previous presentation, one of the panelists was trying to put that we should not try to include what we had discussed. That's why I decided to just go on a progressive work that had added on in the name of the other previous ones.
What I wanted to clarify on is kaolinite.
Yeah.
Kaolinite, it's a clay. Yeah? But this clay, it's kaolinite because kaolinite is white. Yeah? So don't say that it is from the clays that you get the kaolinite. Kaolinite is one group of clays. There are 5 groups of clays, but kaolinite is one of the groups of clays. Okay? But it's got from the minerals, the aluminium silicate you see, rich in feldspars. That's why it is called feldspars. So the feldspars are being washed from there. When they are worked upon, they form the kaolinite as a clay in the sediments. So kaolinite itself is clay. So it is not the clay producing what? Another kaolinite, yeah. That is the clarification, yeah. But the kaolinite comes from those sediments because of the aluminium silicates, but rich in this sodium potassium. So that's why they are feldspars. Okay, thank you, John. And I hope that next time.
Correlate SPT and shear wave velocity. Specific objective number 1 is to develop an empirical relationship between shear wave velocity and SPT value. Then to evaluate the effect of correcting SPT any value and other factors affecting the relationship. The third objective is to compare the developed relationship with those reported in literature. The methodology followed has been summarized using this flowchart. As you can see, we have seismic survey was conducted using multi-channel analysis of surface wave technology, and thereafter boreholes were drilled within a radius of 6 meters from the seismic survey lines. Then samples were taken to determine the densities, bulk densities, and SPT tests was carried out inside each borehole. This photograph shows the cable containing geophones for data acquisition, seismic data acquisition. Then this map shows the location of the boreholes drilled. As I told you, the boreholes were drilled in the vicinity of what? Seismic lines. 28 boreholes were drilled in total, and information from these boreholes is going to be correlated with that from seismic survey. This photo shows drilling at one of the sites. Here I was setting up what? A drilling rig at one of the drilling points. Analysis of results. SPT any values and shear wave velocities were not measured at the same depths. And since we are correlating SPT and shear wave velocities, we had to align these two. Shear wave velocity profiles were transferred into equivalent SPT values using the weighted average, measured at the same velocities, to make sure that at the velocity of 2 meters, you have the corresponding shear wave velocity. So we got pairs at the same depth. Regression analysis. A total of 273 regression data pairs between shear wave velocity and SPT values were recorded. As I mentioned earlier, majority of the published relationships are based on saturated soils. I have a table summarizing publications, most of the previous relationships are always in terms of this, where you have shear wave velocity and SPT and value. A and B are correlation coefficients. As you can see, for example, in Mann, 1970 came up with this relationship. This was work for all soils, but it's only applicable to Japan. The same applies to other researchers. Most of these relationships are region-specific, but the relationships are always in this form. Now, like I've told you, SPT practices and measurements vary around the world. For example, the method of releasing the hammer, how the hammer is being released, the size of the anvil, and the length of the rods vary. And for consistency reasons, it's important for us to correct these values so that they are similar. To do that, we need to correct the obtained field SPT any value. This is done by correcting it for energy losses. To do that, a corrected SPT any value is denoted by N60. There are factors, standard factors for given SPT equipment. In this study, the equipment I used had these specifications. The correction factor for hammer energy was 1, then rod length was greater than 0.75, varying from 0.75 to 1. Then sampler configuration, we used a correction factor of 1, and then borehole diameter, we used the correction factor of 1.5. Research has also shown that SPT value, both SPT value and shear wave velocities are affected by the overburden pressure or effective stress. So there is need also to do what? There is need to correct for overburden. According to year 2001, the shear wave velocity and SPT any value are corrected using the following equations. As you can see here, to get the corrected shear wave velocity with respect to overburden pressure, we use this factor. This is atmospheric pressure over effective stress to power n. Then for SPT, to get the corrected SPT any value, it's atmospheric pressure over effective stress to power n. But the challenge is N and M are empirical constants. They vary from one region to another. They can also depend on the type of soil, degree of cementation, and plasticity. And for this reason, we cannot reliably correct both SPT any value and shear wave velocity, since these two factors vary. In this research, this SPT any value and shear wave velocity were corrected for overburden by incorporating in the overburden correction factor indirectly. This is how it was done. As I told you, the relationship between shear wave velocity and SPT any value is always in this form. So now, like, if we multiply the correction factor for overburden by shear wave velocity, this is what we shall get. Then expressing that equation in logarithm form, we get this equation below. My relationship is a little bit different from the previous relationships in that I'm incorporating in what the overburden correction factor, which was ignored by previous researchers. From this equation, I'm going to use the method of least square regression to determine these coefficients. That's what I'm working on, and I expect to be done like in a week's time. My discussion, the rest of my discussion will depend on what I will obtain from the model. As I mentioned that my overburden correction factor was not directly applied to VS and N SPTN values. But the beta, the beta 2 function caters for that. Further work, I'm going to develop the regression equation in the next 1 week, and the rest of the discussion will depend on this equation. I will look at the effect of overburden or correction of VS and SPT value. Then I will analyze the residues to see whether to determine the significance of my data. Then I also look at the effect of omitting the overburden effective stress term. Then I will compare the developed relationship with those published in literature. Then I will make conclusions. I would like to acknowledge the following: Talo Oil for funding the program, and the CFK for coordinating the scholarship. I want to give thanks to my supervisors, Dr. Anthony Dudu and Dr. Omar Ogamhad.
Thank you, Robert. Can you stay here, get your pen, and then you maybe take some comments? John?
Yeah, I think we go to materials and methods. Yeah, they had corrected that one, I think, from the previous present. But again, on the outlay of the flow diagram, what you're doing, I think it needs some gymnastics. It needs some editing, and of course, even to your entire equations that you have used in your presentation. I think it's good if you can rewrite them using maybe the equation editor. I think it puts it better.
I use the equation editor.
And you copy them and paste them in PowerPoint. Do it directly in PowerPoint.
I do it directly in PowerPoint.
Yeah, they look a bit clearer.
Yeah, then when we go to the map,
This one.
I'm seeing yellow and red, but they are not described what you actually mean. I think it's good if you can put there like a key. Then on your table, of I think some previous literature, something like that. Yeah, I think you could extract like a few, and maybe that one can be like maybe in your literature review or something like that. And that relationship that you're trying to put there, maybe I think you could put it like maybe at the bottom of the table so that it's not confused with what's there. I mean, in my opinion.
Which one?
Yes, AN and
Okay, here I was just trying to show that most of these relationships are in this form.
yeah, but I think it's best if you can put it like at the bottom to avoid confusing people what's there. Yeah, I think that's that.
Some more comments?
The comment made on the effective stress and overburden pressure. Are they exactly the same? Effective stress and overburden pressure.
They are not the same. Maybe let me define the effective overburden pressure.
Yes, you define all of them. You define them.
I define what?
All of them. Because you are defining something. You are saying effective stress. Then again, finally true overburden pressure. So that's why I'm asking. Are they the same? Or?
Okay, they are not the same, but in this case they are the same.
Yeah.
Yeah.
What makes them the same in this case?
Okay, overburden pressure is the pressure due to the weight of the soil.
So on top, yeah.
Exactly.
Then effective pressure.
Effective stress is that pressure exerted on the soil at a certain point.
It has a difference with the depth because it also includes the pore pressure, those pressures.
Yes. But now, like in this case, there is no pore pressure. Yes.
Yeah, then you should define why you're saying effective stress different to overburden pressure because the other elements, infections that are missing, which brings it again up to, which makes it the same as pore pressure. Then maybe the other thing, I don't know if you consider with depth because look at overburden pressure, it varies with depth of overburden, the thickness.
Of course.
Yeah, so I don't remember you mentioning it, so maybe you could make a reference and say overburden pressure at this depth.
Definitely it has to be at the depth, it has to vary.
Yes, but you need to tell us that it varies with depth because it is not stated explicitly in the presentation.
In limited detail, it varies as in its factor.
Yeah, just say it.
But it really varies, it's a fact.
Yeah.
So that's why I didn't mention it.
Okay, no? Yeah. I have a few comments. We'll begin with the title. Yeah. What is this? SPT.
SPT is standard penetration test.
And why do you abbreviate it in the title? Abbreviate.
No.
No? Because we don't know it. The first mention should be all of it. When you first mention it, because it is appearing the first time. So we can't know. Unless when you were writing somewhere and you have mentioned it, then you can abbreviate it. Okay, let's continue. The next slides. Specific objectives, number them, eh? Don't put blades, number them. You see that it is one, either Roman numeral or the 1, 2, 3. The other comments already have been said. Robert, for sure now, I can't assess how much work you so far you have done and what is remaining. Yeah, because you are giving us just a small bit of it. And we wanted to know how far are you. For example, the background, the literature, how much of that work have you so far done? So that we assess that you are within the time of the thesis completion. Are we near the end of the thesis or?
Okay, why I left out the background and the literature review? Last time we were told not to include it.
No. It was an improvement of last time. So we need the whole work. So just like the comments of John, in the next presentation we want to see the whole work. Then we can know that so far you are here and this is the bit remaining. Or near completion or you are not completing within that given period. So it is a fact-finding presentation that we need to know that this work you will complete or you won't complete. Yeah. So the next presentations, please make sure that all the work, just as what Christine gave us, you know that this is covered and this is what is remaining, briefly. So within these 2 remaining weeks, we want to see that. Thank you. Thank you, Robert, for your presentation. And we hear from our second lady. Proceed. The first lady? No, the second lady.
But using interferometric synthetic aperture, which I will keep on referring as INSA in the following text. I'll just give a brief background. Velvet engraving is a region of heightened seismicity. As we can see, some of the events, earthquake events that have taken place. And ground deformation is a phenomenon that is related to earthquakes. Yeah. So now, what I'll be doing is stated. What I'll be doing this study is stated in my problem statement. Ground deformation has been carried out using the traditional geodetic techniques, which include leveling, GPS. But these are point-based and very costly if you're going to carry out ground deformation for a very large area. That's why I'll explore the use of INSA, which INSA has the capability of analyzing ground deformations at a large spatial resolution. So the objectives of this study, mainly it is to use INSA to assess ground deformation in the Albertine gravity. As I've told you, assessing it due to this is listed in the area. But specifically, I'll be using historical satellite data to do this analysis. And the objectives, and I will have to number those again, I've noted. The first one will be to find out, is there actually any ground deformation in this area? Yeah? Then, if there is, find out, find evidence of ground deformation, then identify those areas. Then the second objective will be to quantify the deformation. Then the third is to compare the deformation with seismicity. So, data and methodology, I'll first describe the study area. The study area is the one that is shown by the white polygon. That is in the police exploration area. Yeah. Then I started by acquiring the data, earthquake data. I went to the United States Geological Survey earthquake catalog and I picked out events, earthquake events that have happened for the time period 2007 to 2011. And that is the table we are seeing. But I went ahead to split the earthquake events into intervals so that I do a ground deformation analysis for each interval, since they are occurring in different time periods. Yeah. Then I went ahead to acquire satellite imagery, which is also shown with the specifics, the specifics of time, the incidence angle, the orbits is all mentioned there in the table. So I was lucky to get many images, but from these many images, I had to choose the ones I'm going to actually work with. So as a criteria to choose from the many images that I had, that is the criteria I used. I had to look for the ones that have shorter perpendicular baseline. Baseline is when the image is taken from a satellite, you have one antenna and another antenna here. So that this distance between the two antennas affects the results that you obtain. That's why a shorter perpendicular baseline is required for the images that you're going to use for interferometric processing. So I went ahead to find out what the perpendicular baselines are, each for the images that I had, and the ones that were suitable are the ones that I actually picked out to use. So the processing was carried out using MV software, which was generously contributed by my supervisors. Before I go ahead, let me just describe how INSA works, so that when I go ahead to explain what I found out, we can all be at par. What happens is that you have an area. So we have a satellite in space. So there's an electromagnetic energy that is sent to the ground. So when this energy is backscattered, it is recorded as an image. An image which is a grid of pixels. It just records how much energy has gotten back depending on the properties of the area that it will meet. Yeah. So after some time, the satellite will take an image of the same area. Yeah. And also the satellite will be using, for example, it will be revolving on the same orbit. It will not change, for example. So it takes another image. For example, if there has been ground deformation, you see that there's star, I mean with the
Right.
star. So you see that after some time, if there has been any deformation, it will be recorded in the next image, because the image is as a result of the range distance from the satellite to the target. So that's how we get the deformation using those images. So now that is the flowchart of how the processing is done. You have, I obtained raw data, then I converted it to single look complex images by just focusing the energy into smaller pixels. Then after, I go ahead to co-register the images. If I have an image that was taken before an event, earthquake event, and another after an earthquake event, I go ahead to register them so that they are all they are corresponding with they are all corresponding geographically, so that I don't have a shift. Then I go ahead with the interferogram generation, then flattening. Flattening, I am removing the phase due to the earth curvature. It affects the result, so you have to remove it. Then adaptive filtering and coherence generation. Adaptive filtering, I'm removing the noise. For example, they might be haze, so you have to remove it so that you can be able to interpret your results. Then I'll create differential interferograms and coherence images which give a guidance on the quality of the results. Then phase unwrapping, then finally the displacement map. So this is how it will be done. It will also be shown in the results. So data analysis, as I already mentioned, I split the earthquake events into 3 intervals, and I was analyzing for each interval. So for the second interval, it is May 2008 to November 2009, and it had earthquake with magnitudes of MS4 and MS4.5. Then those are the images that I used. For this, I used 3-pass interferometry. So, using the first 2 images, I create a digital elevation model, which digital elevation model is supposed to give me the topographic phase that I'll be using for the final differential interferogram generation. So that is the interferogram, that is the DEM that I created from the images that I had, and the height varied from negative 608 and plus 685 meters. So I went ahead now to generate the differential interferogram. Now from the differential interferogram, you're able to tell if there has been any ground deformation between the time period you're analyzing. Now in interferograms, what we do, differential, you just count the fringes. Now the number of fringes, you multiply them by the wavelength of your satellite divided by 2. So from there, I counted those are 2 fringes, and then I multiplied by the wavelength of the satellite, which is 23.6 centimeters, and divided by 2, and came up with a ground deformation for this time period of 0.236 meters. Yeah? Then I went ahead to create a displacement map, to find out which areas have moved. And that is the image that is shown there. So the deformation, it varied between negative 0.3 meters and 0.32 meters, but with an average for the whole entire scene of negative 0.06 meters. But when I went ahead to locate those areas of red, which correspond to high deformation areas, I actually found out that those red corresponded to areas of where the well locations are. They were Ringi, the Kasameni, the Ngiri. Okay, this is a smaller scale, but the other one, I found that there has been change in land use. There's a lot of earth movement that has taken place, and that's why it had to be picked out as a change in ground. And that's why the other one is also noted as a ground deformation. So I had to go ahead to assess what is the quality of the results that I have found. So in Insta, we use what we call the coherence image. It shows you which areas were consistent in quality for the 2 images that I used. So generally, the coherence was 0.2, the highest was 0.86, which is shown by the lighter pixels, and then the dark ones, which is 0, it means those areas are incoherent. It means for the 2 images there was a change. Yeah. So low coherence, when I went out to find out what happened to the black areas, some of them I found that there was change in land use, and some of them there were vegetated areas. So I went and did the same thing for interval 3, and then that was the DEM that I created. Then the interferogram, again I could count 3 fringes, and then from the fringes I find out what deformation it was, which was 23.6. There's a mistake there. That is centimeters, not millimeters, I'll correct that. Then again the displacement map for the same. So for this I found out that the deformation varied between negative 0.25 and positive 0.26 with an average of negative 0.13 meters. Again, I went ahead to do a quality assessment of the results, and I found that the average coherence was 0.24. Then I had the conclusion for each. I concluded following the objective. The first objective was to find out if there's ground deformation in the area, and then identify those areas. Yes, the color fringes that I saw in the interferogram are evidence that there's ground deformation, yeah, which I went ahead to quantify. So for the second interval, the deformation was between negative 0.37 meters and 0.32 meters. Then the third objective was to find out if there's evidence between ground deformation and seismicity. For this case, I noted another mistake. It was not easy. I missed that. It was not easy to specifically find out if the deformation that we noted was due to seismicity, because there are already other activities that were carried out, like the pad construction, that already came out as deformations. That's why I could not explicitly state that it is from the seismicity of the area. I went ahead to conclude for the third interval still, the deformation in the area varied between negative 0.45 and plus 0.026. Then again, it was not easy, because even for that time interval, I got an Excel sheet of different wells, and when they were constructed, and actually found out that between these time periods, there were wells that were constructed, which came out to show deformation. So now, I had to conclude that INSA itself may not give an absolute answer to whether there has been ground deformation or not. But when we combine it with other geodetic techniques like GPS, like leveling, then this should be able to give us a comprehensive answer of whether ground deformation has occurred or not. I did not mention in my last slide, but the next interval that I have to do is interval 1. Now in interval 1, there's been no pad formation, no pad creation. It is an interval where there's been no disturbance on the ground. What has delayed me was getting the digital elevation mode, high resolution digital elevation mode. I've not been able to obtain this. What we have is of lower resolution, but now that we failed to obtain one that is of high resolution, I'm just going to go ahead and use that, and then do the first interval, and then I think I'll be through. Thank you very much, guys.
Thank you, Pussy. You stay there. Maybe you pick up your pen, and then they'll give you some comments. Quick, brief comments.
Maybe some comments are relevant on your methodology. You said data methodology. It was rejected for me last time. Yeah, so it has to be considered in the graduate school guidelines. Either it is materials and methods or methodology.
It's materials and methods.
Then when you show the other map that showed where you have your blocks and
my blocks.
That one.
Yeah.
From your discussion, it seems that you were interested only in the white block.
Yes.
So why do you put the blue ones? And if you think we should see them, why don't you define what they are?
Okay.
Yeah, you tell us, maybe you put in label, say this is this and this, so maybe it is very important or not.
Okay.
Yeah, and you were mentioning the MS. Maybe people may not understand what MS is, so you need to tell us. And one more observation I made that the font on your slide is not consistent.
Okay.
Yeah, you have different types of fonts and probably different sizes, and some slides are too congested.
Okay.
Yeah, we find trouble trying to read what is there. Thank you.
Robert, some comments?
Then I also observed when she's presenting, she keeps saying, this was a mistake, this was a mistake. And this is the only time she has done that. I think she should try to.
Yeah. Other than telling us actually my work is full of mistakes. We may not trust you.
Okay. Yeah. That one I
Just keep quiet and we move on.
Okay. Okay. Thanks.
Christine, you have something?
I look at some slides are not numbered. Some slides.
Yep, there's number.
Hey, some are not numbered. Okay. Consistency.
John, something?
No?
Yeah. I will ask that map, you drew it yourself?
No.
Mm.
This I obtained from Talo.
Yeah, you should acknowledge them.
Okay.
Have done it for you. And you are not putting the place, we can't tell.
Yeah.
Normally maps we have scale.
Yeah.
We want to know how big the area is and the like. To most of the things that have been talked about, what I would want to find out, how far have you gone?
I'm almost. I got the dam now, so I'll be working this week. I'll be working on the last part.
The last part. Two, I don't know how you present your data because what you gave, what I got is that you went through a series of things.
Yes.
And then this series, are you putting a final table telling us of each area?
Yeah.
Okay.
I give the final.
The final one. Okay. Because what I saw was a series that this I've done for this, I've corrected for this, I've corrected for this, and then you get the images, maybe of one particular place.
Yeah.
And then we will have a table showing us what happens on the other one. Just as Barnabas said, I see you are saying MS4, MS5. What is MS?
That is an earthquake magnitude measure for surface earthquakes.
Yeah, because I was about to ask. You know, we are usually we know the Richter scale.
Yeah.
So, how do they differ? The other one is for surface.
Surface.
So, thank you, Pros, and the.
I'm doing is seismic hazard analysis for the Albertine region, and this study probabilistic approach is being used. Doing a recap of the objectives so that you can have a clear view of how far we go with the study. And basically the main objective was to do an assessment of the hazard due to earthquakes in the Albertine region. Specifically, the first one is to identify and characterize the seismic sources where these earthquakes originate. And the second one will be to determine how the ground motion due to these earthquakes transverse from the source to an area of interest. So we look at maybe the attenuation of the ground motion. And finally, look at determining the recurrence of the mean peak ground acceleration. This is a measure of ground motion that has been chosen for this. There are others like the velocity or the spectrum. So for this study, we shall use the peak ground acceleration. Basically, we look at the methodology. Maybe let's try to take this one. It includes looking at the catalog, the data itself, and then the process that is being used is the probabilistic seismic hazard analysis. So the first thing is to look at the seismicity of the area, which helps us. And these slides are showing us the seismicity. This shows us the epicenters of the earthquake events. And this is just a swarm of events. Specifically, this first figure is showing us the small events, those magnitudes less than 4 on the surface wave scale. And the next figure shows us those ones that have been chosen in the catalog. These are magnitudes from 4 and above. And 4 was chosen at the data because it has been proved that earthquakes of such magnitudes below 4 do not have adverse effects on the engineering structures. So 4 was chosen as the lowest bound magnitude. And in that figure, it shows the distribution of those epicenters, those earthquakes that are used for this particular study. And just as I mentioned in the methodology, the earthquake data compilation includes instrumental epicenters. We look at what has been documented by different agencies of the earthquakes in the region, and because different agencies report in different magnitude scales, there's need to unify them. And for this particular study, the surface wave magnitude scale was used. So it means all other scales were converted to, so using different models. After that, we look at the distribution of these earthquakes in size, that is the magnitude ranges, but also need to look at the time factor. How is our catalog complete? Does the catalog record all the ranges of events from the time of the catalog start to the end of the catalog start? And then after we look at their distribution in space, that is, look at their epicenters. Where do they exactly occur? Once that one is done, then the next thing is to characterize our sources. That's to look at the geometry of the sources, depending on the characteristics of each source. We take, for example, a seismic source to be a region where a given, let's say, magnitude of earthquake has the same probability to occur at any point within that source. So that's why we do source zonation, look at the parameters that define that. And at the same time, we look at the recurrence of these earthquakes, where we determine by the Ritenberg Richter parameters, that's the B value, shows us the proportion of big events compared to the smaller events in a given area. Then there's review of and selection of existing attribution relationships. These ones need strong motion data. It means there must be records of earthquake events for a long period of time for it to develop an inclination model. And because of the absence of such, it means models that have been developed before for similar regions or within the same region were compared and then find out which best suits the study area. And once that one is done, the attribution relationship is developed. And finally, the hazard analysis, which is done using the probabilistic seismic hazard analysis method. Okay, so for the data convolution, the frequency distribution of earthquakes is plotted. This shows us the magnitude ranges with the frequency. Now, it's assumed that if there is consistency in the occurrence, or if all the ranges have been recorded, this relationship will produce a straight line. Now, where there's variation from the straight line, it means that the period before that, or for those ranges, the catalog is not complete. So it means for some period, those ranges are not recorded. Now, for this one, for example, can be shown that our catalog is complete for magnitudes from 4.5. So it's only these ones that can be used for the analysis. But also plotting the time magnitude plot. It can be seen that, for example, if you look at magnitude from 4.5 and above, you can see that there are events all through from 1900 to 2010, which is the time for the catalog. But for the events just below that, you can see that for magnitudes less than 4.5, they are concentrated between 1980 and between 2000, say like 5 up to 2010. And it was noted that actually from the sources that during this period there was a grid of seismometers that were laid in the Albertan region by the geological surveys. So it means a large sum of smaller earth crisis 2007 will be used for the analysis. So after putting all these parameters, that will be run and then we will determine the hazard for the given area, and then the maps will be generated. Thank you.
Thank you, Barnabas, for the presentation. And I invite some comments, questions, clarifications.
Barnabas, yeah, I want to ask. If it's a value, B value, do they have units or their dimension?
No, they're dimensionless. They're just parameters. They're just regress factors. Yeah.
It has been clear?
You've understood or you're confused?
You have understood? No, you have not understood. Thank you, Barnabas. I would ask you how far we are with our work.
My work,
How far, yeah, with your work?
I've finished the first two objectives. I'm left with the third objective, which is the final objective.
Yeah.
And I think I'm 80%. done with the whole work.
And the write-up, you are...
The write-up, I do analysis with the write-up, so I do my objective and make the write-up at the same time. Yeah.
Thank you, Barnabas, for the presentation. Yeah, thank you. Good go. Let me take this opportunity to thank all of you for your time, patience, and the work so far done. Because when we started, we didn't see what we could get to up to this stage. You remember very well what we have gone through and all those bottlenecks which we have cleared, and now we can present this work. But I also want to urge you that we need to get to near completion of the work, and we are having another presentation of the complete work, and now here we are inviting other people to listen to the work. Now we want you to give the expertise. You do how you begin the work, the literature review, problems, the objectives, the materials and methods, how you have the results, and how you discuss your results in relation to the literature. And then that one will give us a basis of what is estimate of the time when we have to complete this work. So that's what we want to see in the next presentation. Otherwise, on behalf of the CFK and my colleagues, we thank you. Of course, we don't forget the generous support from Talo Oil. You are supporting all this work. So thank you very much. So at the end of this month, only you remember that you have to be ready for that. I will not make any other announcement, but let's agree that at the end of this month, we meet again and we have other people listen to the work we have been doing for the past 1.5 years, something like that. Okay? Thank you for today.